All right, well, welcome to Chapter 7 of Calculus, and this is where we begin our journey in Calculus 2 by taking a look at everything we've learned from Calculus 1, and specifically the last part of Calculus 1 where you learn about the definite integral, and we're going to take that information and we're going to apply it. So Chapter 7 deals with all of our what we call applications of integration. And so we'll be looking at all the different things that the definite integral can answer for us. We'll look more specifically a lot of times at geometric things. So we'll talk about area, volume, surface area, arc length. We'll get into a physics application in work. But for right now, we'll start off with talking about area between curves. And so we pick up where we leave off in Calc 1, and now we're going to run with that and look at some applications of integrals. And so before we get started, I reminded us of what we learned at the end of Calculus 1, which is the fundamental theorem of calculus. The fundamental theorem is a relationship, again, between the definite integral and antiderivatives. This two-way relationship that says, hey, in order to calculate a definite integral, remember what a definite integral is, all those rectangles under a curve, and you're letting infinitely many rectangles be shoved underneath there that are infinitesimally small. And instead of calculating it that way with all those sums and Riemann sums that we discussed in Calc 1, instead, if you want to answer that question, there's a relationship which requires just knowledge of antiderivatives. And so it's the best shortcut ever, and we use it to our advantage, a lot in Calculus 2. And so I remind ourselves what it is, the fundamental theorem of calculus. Starts out with a function that, of course, is continuous, right? So no gaps, no breaks, no jumps, nothing weird going on. Let f of x be continuous on this interval AB. And capital F represents an antiderivative of little f of x. Then the definite integral from a to b of f of x dx, this whole rectangle thing that you add up, is equal to the difference between the antiderivatives evaluated at the endpoint. So capital F of b minus capital F of a. And so this is where we leave off in Calc 1, this kind of culmination. You learn all different ways to take antiderivatives, evaluate definite integrals. And now what we're going to look at today is we're going to look specifically at area. Area between curves. And it's very important that I use the word area. The thing about area, if I say area, it implies a positive quantity. Area is positive, it's a measurement. The thing you know about the definite integral, at least hopefully you do at this point, is definite integrals don't need to always measure area. They don't always necessarily give you the area under a curve. Remember, if you're drawing rectangles, if those rectangles are below the x-axis, that's negative, quote-unquote, area. If they're above the x-axis, that's positive area. And if your curve stays above the x-axis the whole time, then yes, you can say it's area. But if that curve starts to go below the x-axis and back up above the x-axis, you could get negative definite integrals. You could get 0 for a definite integral if there's the same amount of area above or below the x-axis. And so we see that definite integral doesn't always measure area. And so it's very important that I use the word area between curves here because it's going to lead us into how we're going to discuss how we're going to measure area between curves. All right. And so let's take an example. Let's draw it and try to get some fundamentals. What we're going to do in this video is we're going to get the fundamentals of how we're going to calculate area between curves. And in the next video, we'll look at some examples, right? We'll work it out and actually put it into some practice. So right now, we'll keep everything kind of general. And so I'll draw a plane, XY plane, and I will draw two curves. So say f of x is this guy here, and g of x is this guy here. And say those curves intersect at 2 points here and here, A and B. And say we wanted to find the area of the region shaded in between these two curves. Area bounded by these two curves. So that's kind of the terminology we'll use. You want to find the area of this green shaded region bounded by these two curves between A and B. And so how are we going to measure area? Well, we can't just integrate from A to B f of x because that would give us too much area. If we look at g of x, well, we're going to have some below the x-axis. That's going to give us something negative. We don't want that. how are we going to measure the actual area, a positive quantity that represents the green shaded region? And it really comes down to the very simple idea of measuring distances between 2 points, or the length of a straight line. And so let's go over here on the side, and we'll just kind of do some homework before we answer this question. And remind ourselves that we have the ability to measure the distance between 2 points. And so if I take a number line, say A here on the number line, and B here on the number line, and I wanted to know the distance between A and B, what is the length of that green line, or the distance between A and B, we would say the distance is B minus A. B minus A is the distance, or the length of that green line. Why is it different? Well, difference is subtraction or displacement. So this is going to measure the difference between B and A. How do I know it's positive? Well, I always will take the bigger value minus the smaller value. The final minus the initial if you're a physicist. The bigger value minus the smaller value. And that will give me the distance between those 2 points. Even if I change the orientation of my number line, even if I measure it vertically, actually this will make a little bit more sense. B and A here. If I wanted to measure the distance between these 2 points, or the length of this green line, again, it would be B minus A. That would be the length of that green line, right? The bigger value minus the smaller value, the distance between these 2 points, the displacement. Why do I bring that up? Because, well, trying to find the area of this region is not so easy. It's not a nice geometric object that I can find the area of, but instead, let's just think about a generic x value between A and B. So some generic x value in this interval between A and B. And say instead of trying to figure out the area of this region, let's just look at some outputs of the function. Let's look at the output of x here. That would be f of x. Or sorry, g of x. Sorry, we forgot to label g of x here. And the output of this parabola here, which we call f of x, let's look down here, that would be whatever f of x is. So if I look at a generic x value, the output on the top curve is g of x, the output on the bottom curve is f of x, and I look at those 2 points in the plane. And just like we did here a second ago, you could tell me the length of this blue line. The length of this line, or the distance between these 2 points. And just like we did over here, the distance, or the length of the blue line, would be g of x minus f of x. The distance between them. And that would actually measure a distance, a positive quantity. Even if f of x is negative, then I'm going to subtract a negative, which is going to add something to this, right? Minus a negative, so it's going to add something. So it's actually going to give me that now distance between the two. G of x minus f of x. Right here, it's irrelevant, right, where 0 is. It doesn't mean that A and B are positive. They could be both negative and still measure distance. And so g of x minus f of x gives me the length of the blue line. And in fact, for any x value in this region, even if I put x, say, over here, right, we're still between A and B, and I look at x over here, right, we have the output for x, g of x here, we have the output for f of x here, right? Plug them in. And say again, we wanted the distance between those 2 points at that given x value. Again, it would be g of x minus f of x. So in all cases, for all values between A and B, the distance between the points on these curves are g of x minus f of x. So we can measure the length of the straight line, that positive quantity. Now, the beauty of calculus is you learn that if you want to measure the area under a curve, how do you do it? You add up infinitely many, infinitely thin rectangles. And that gives you the definite interval. And in this case, an infinitely thin rectangle, that's really a straight line. Infinitely many, infinitely thin rectangles, that's a bunch of straight lines. And if we apply that now here, we can find a way to measure this area, not by thinking of it as a whole, but thinking of it as infinitely many, infinitely thin pieces. Right? Because now all I'm going to do is I'm going to add up all the length of these straight lines. from A to B. I will measure the length of every single straight line between A and B of this region. And I will glue or integrate, that's what integration means, makes the many parts one. I will integrate all of those straight lines together to make the solid, to make the whole. That's exactly what you did in Calc 1 when you learned the definite integral. You measured rectangles, you made those rectangles smaller, you put more and more rectangles, you eventually got the region itself. That's the same exact principle I'm doing here. And so how do we find the area between these curves? Well, if I want the green region, I need to integrate all of these straight lines together, glue them all together. So the thing I'm going to be gluing together, the lengths of these lines are always g of x minus f of x for all x. That's the length of all of these lines. I'm going to integrate all those lines together, starting at A, so that's where I make my first little line, continuing all the way to B, summing them all up, as I slide along the x-axis. Right, we have an infinitesimal base to our rectangle in a sense, right? So we're moving along the x-axis. We can think of these as infinitely thin rectangles or lines. The rectangle's base is dx, infinitesimally thin, so a line. And I'm going to add all these up. And now this gives me the area between the two curves. A couple things to observe that's important. If we want to actually measure the length of this straight line, since it is subtraction, it's very important which curve goes first. This is the larger or bigger curve. And this is the smaller. Larger minus smaller, bigger minus smaller. The one with the larger output minus the one with the smaller output. That's very important. Now, of course, this leads to some fundamental questions. Okay, that's great, but what if we have a scenario? What if we have a scenario where the curves switch? What if I'm finding the area between two curves and maybe one of the curves doesn't always stay the larger curve? What if they switch at some point in my region? And so let's explore that just for a second. So say now, and again, we're keeping everything generic. We're going to do some examples in the next video. We're just getting the foundations right now. Say we have something like this. And we're not going to get worried about labeling these curves specifically. I'm just going to call this a general f of x here and a general g of x. Yes, one is cubic and one is a line, but it's not important right now. And so what if I want to find the area of the shaded region bounded here by these curves? The area is shaded in green. Now it's important to realize that, okay, well, they have one intersection point here, A. They have another intersection point here at B. And they finally have one intersection point here at C. Now, if I wanted to, again, measure the area shaded in green, it would not be as simple as just integrating from A to C the difference between these functions, like we saw in the last one. Because if I break it down step by step, if we start to measure straight lines, so if I take a generic x value between A and B, we have f of x and g of x. And I measure the length of that straight line, that would be the difference of top curve minus bottom curve, or the displacement larger minus smaller. That would be f of x minus g of x. So the lengths of straight lines in this region between A and B are always f of x minus g of x. And so to find part of the area, we would integrate from A to B, and we would do f of x minus g of x. So we're going to add up all those straight line segments as we move along the x-axis from A to B. That will give me this first green shaded region. And at B, I have to add another integral, because if I go f of x minus g of x here, that's not going to work. if I take a generic x value between b and c, and I look at the outputs of the function, the g of x curve is above the f of x curve now. And so if I want to correctly measure the length of this straight line, I would have to do it as g of x minus f of x, larger minus smaller. And this time they switched. So that means if I want this area as a whole, now I will integrate from b to c. I'm not changing the curves, they're the same functions in this plane. The only difference is the order that I need to write them. In this case, it would be g of x minus f of x. Dx. This will represent the length of these straight lines between b and c. I'm going to add up those straight lines as we move along the x-axis from b to c, generating this entire shaded region. So I'm not changing the curves, I'm just changing the order they're written because it's very important since this is subtraction. Since I'm subtracting these values, measuring the distance between them, that it's always larger minus smaller. And if they ever switch in my region, it's very important that we subtract in the right order. And the general order is always larger minus smaller. And so if we want to find the area between curves, this is how we are going to do it. A couple things to keep in mind in terms of the setup. So how do we do this? So finding area between curves, a couple things to remember. One, the first thing I need to know is the bounds of my region. What am I integrating over? So determine your bounds and intersection points. Bounds / intersection points. In some cases, you are just going to be given a bound. Find the area between one point and another point, 0 and 4, 1 and 5. It may just say find the area bounded between two curves. In that case, find where they intersect, find a naturally bounded region. So determine bounds or intersection points. That's also important because, hey, if I am given an interval to find the area between, I would need to make sure that, hey, what if they switch somewhere in the middle? So I would need to find intersection points just in case they make a switch, and then I would need to set up two intervals. So determine bounds or intersection points. 2, determine which function is larger. Function is larger in each region. Right, so I have the intersection point. If they just have 2, we have 1 region. If they have 3, we have a couple regions. So determine which function is larger in each region. Because we're going to need to measure in the right order. And 3, measure the line segments and integrate them together. This is the general process in which we'll find the area between two curves. Determine the bounds or intersection points, determine which function is larger in each region, measure the line segments, right, that's the distance between the curves in each region, and integrate them together. That is the general process map for area between curves, and that's how we will do it. So in the next video, what we'll do is we'll come back and put this now into practice. We'll do examples and see this worked out with very specific functions. All right, thank you.